He was hilarious. I love that scene. It's great.
All right, guys.
That entire scene with her knocking him out and everything.
So this last little problem set here, it's the last one before our test. So we're gonna go quiz test, because this will be our last quiz in the what we call maybe unit 1. And then we'll move on to unit 2 next. 2.1, 2.2, 2.3. So if you have understood the last thing we were going over, all those graphs, this will be extremely easy for you. If you have not understood that, this will be another opportunity for you to make sense of it. So it might finally click for you as we're going over this. It might be like, oh, I finally understand end behavior. Oh, it's finally makes sense. So hopefully that happens for you if you've been confused. This guy. Now we're going to also open ourselves up to a few different types of functions that we haven't looked at, but these all have something in common. They all have symmetry. Okay, so the title of this is even and odd functions. This guy. Let's just start with this. I'll tell you, this is an even function. This is an even function. Now, this is just a fancy word for y-axis symmetry. So it's actually nothing really new. We've dealt with symmetry in school for years, right? Y-axis symmetry means that there's a symmetry across the y-axis. So let me show you what I mean by that. Let me pick an x value. I can pick any number I want, really. How about the number 2? If I plug in 2 into this, that comes out. 1/5. Everyone okay with that? Now, who thinks they have a guess? If I'm investigating y-axis symmetry, what's the next number I'm going to plug in?
4.
-2. Very good. Okay. -2. So think about the way axes work, right? There's 2, and then -2n. Square it, add 1. You also get 1/5. This is what we're talking about. It's just easier, if you're wondering why I invented a new word, it's just easier, talking about a function to say, oh, it's an even function. That means is that any point that lives on your graph, so here's some random point, where's his best friend?
On the other side.
On the other side of the y-axis. So it's a sign of reflection, okay?
Mm-hmm.
So like, for example, this could have been the point 2 1/5. Now it'll be the point -2 1/5. So the big idea is two opposite x values would generate the exact same input. Not too confusing, right? All right, now let's get into the hard part of this, which is what does a graph look like? Well, someone tell me the meaning of this.
X is greater?
Very good, Zarita. All rails. So let's think about that. Why is it all reals? Well, can that expression ever equal 0? If I ask the question, how can x squared plus 1 equal 0? The answer to that question is there's no real numbers that do that. So if there's no real number that causes division by 0, the domain is all the real numbers. So that means no vertical asymptotes, right? How about end behavior? What type of end behavior does this guy have? I guess I was looking. Yeah, if you said it's going to 0, you're correct. Yes, so I'm saying the end behavior is similar to that function, that parent function. And so yeah, as x approaches infinity, y approaches 0. As x approaches -infinity, y approaches 0. Are we still okay? No questions? Okay. All right, let's graph it. So the graph, this is one of my favorite functions. I don't do this guy anymore. So I may be missing one extra piece, one really good piece of information that's always easy to get on these kind of things. the y-intercept. What's the y-intercept of this guy? 0, 1. So that's the point 0, 1. And here's where, when you go to graph these, symmetry is really helpful, because if every point has its best buddy on the left side, it'll be symmetrical, as if I folded the paper along the y-axis, the function would fold onto itself. So anyway, if I start here and go to 0, that's going to look something like this. There's me approaching 0. How about the left side? Mirror image. There's my graph. Mr. Humpty Dumpty. Love this guy. It's beautiful. It's gum. Camel hump. All right. Any questions on that, guys?
What makes it an even function?
The y-axis symmetry. So
Does an odd function have x-axis symmetry?
not quite, but it's going to be a different type of symmetry. Maybe someone knows the answer to that. It's not going to be, well, the thing about functions is they can't have x-axis symmetry, typically, because, so, I mean, a set of, like, for example, I draw a parabola like this. You can make a relation like that. It would be something like, it would be y squared minus, say, 4 is x. You can make a locus of points. Did I have that correct? Let me just. A function. Okay. So, I think that's right. Yeah. So, anyway, yeah, not a function. Fails the vertical line test. That would be x-axis symmetry, though. So you can have a collection of points on a graph that have x-axis symmetry. So what's the other kind of symmetry something might have? We call it an odd function, but it's basically origin symmetry. So the next one I'll talk about is, what if every point, so here's a point on a graph, what if,
Cool.
now there's a relation here between this and there's a rotational idea. How you can rotate the function 180 degrees onto itself. But I think it's probably easier to think about it in terms of just every point will have a companion point through the origin that they see. All right, so what does that look like with numbers? Here's a fun question. There's only one odd function on this whole front page. Can you figure out? It's 3. 4 is a little weird because the absolute value ensures that the top is always positive and the bottom is always positive if x is non-zero. Okay, so we're going to look at 3 next. I think it's also kind of interesting to think about. What we're about to look at is what you get if you take this guy and multiply him by x. So kind of a different perspective to take. Okay, this guy, I'm just going to tell you in advance, he's odd. He's an odd function. Now, the chicken or the egg thing. How do I know it's odd? Well, I probably would do this first. I'm going to say, well, let's examine some xy pairs. Let's throw a number in there. How about 3? What comes out if I plug in 3? 3 on top, 10 on bottom. 3/10, also known as 0.3. How about -3? -3/10. Now we see the oddness, right? There's that different type of symmetry. By the way, this is also known as origin symmetry. Or, some of you guys said rotational symmetry. That's also a correct way to think about it. Let's do one more maybe. About like 4. Why not? 4 gets me 4/17. -4 gets me -4/17. You see the idea? Do you guys all understand how this implies that every point on the graph has a corresponding companion on the other side of the origin?
Yes.
You sure? No questions on that? Yeah. All right. Cool. Cool beans. Domain. All rails. And behavior. Well, if I cover up the non-dominant term, what do I got left over? X over x squared, which is like 1 over x. So the end behavior is going to be similar to that famous parent function that goes, it'll be approaching 0 from the top on the right, and it'll be approaching 0 from the bottom on the left. That. How about in the middle? What happens when x is 0?
Y is 0 because x is top.
Yeah, if you plug in 0, you get 0 over 0 plus 1, which is 0. So that means the point 0, 0 is on the graph. If you think about it, any odd function, if an odd function has a y-intercept, it would have to be the origin. Otherwise, how is it going to be symmetrical to the origin? It's not really going to work out. Anyway, so my end behavior, x has to, as x approaches infinity, y approaches 0, same thing on the left. All right, so what, I'm starting here. Where do I got to go? I got to approach 0 in the long run, but I mean, I got to have some positive y values, right? So I got to go up and then down. On the left, I got to go down. And I got to go back towards 0. There you go. That's pretty neat. All right. Do you feel okay about that? No. Okay, so some people have in the past become confused at this point about domain. They go, oh, so you're saying that every even or odd function, well, first, let's go over 2 points of confusion. One is, oh, so you're saying that every function is even or odd. No. Can you think of a function that's not even or odd off the top of your head?
I can't think right now.
Anything that isn't symmetrical.
Yeah, exactly. Literally any function you can come up with that doesn't have this kind of symmetry or this kind of symmetry. So here, real quick. How about y equals 2x plus 1? That's not symmetrical because if you plug in 3, you get 7. If you plug in -3, you get -5. Not even close to symmetrical. So not even close. Did you get the idea? These are special functions. Let's go over one more because sorry, that was the first point of confusion. So no, not every function is even or odd. Only, I think every one in this problem set is. I picked them out as like, okay, these are all kind of weird special functions. Other one is, oh, you're saying the domain is always all rails? Again, the answer is no. If you look at problem 2, what is hashtag reduce, recycle. Now it's number 2.
That's a message for change in today's world. That's incredible. Good job.
Really do my best out here. Thanks. Trying to make an impact, save lemurs.
Thank you.
Yeah. If you're not saving lemurs, what are you doing?
What about the ball?
Okay. Last one, then we'll have some work time. You guys can knock out about yourself, okay? Make sure you understand it. This guy, uh-oh. What's he got that the first two didn't have?
Negative.
Well, yeah, there's a minus sign in there, which means, yes, the domain x can't be 1 or -1. Hopefully by now, we've got this, we understand it, that means there's going to be vertical asymptotes at 1, x equals 1, and at -1. Just looking at this one, do you think you maybe have a rough sense of whether it's going to be even or odd?
No way.
Yeah, it's going to be even. So let's see why. Plug in 3, you get 1/8. Plug in -3, you get 1/8 again. Oh, okay. That right there is pretty good evidence. You can check a second pair of points to make sure. It's always possible to get unlucky and it's not even or odd, and oh, oops, that just happened to be a pair of points. So if you get 2 pairs of points, that's going to be pretty good odds that it's correct. You can try yourself if you want. Plug in 5, you get 1/24. Plug in -5, you get 1/24 again. So this also might give you some hint as to the end behavior, right? So if you plug in a decently big number, like say plug in 7, you get 1/48. Plug in -7, you get 1/48 again. That's giving you a big hint that it's approaching 0 from the top on both sides, right? Like, oh, hey, and so the end behavior is like 1/x². So end behavior, we're asked to tell the end behavior, approaching 0 on both sides. This problem set has a bunch of functions with more interesting end behavior. If you're getting kind of bored with the always approaching 0, there's a couple on here. Especially when you throw absolute values in, you can get some interesting strange behavior. We've talked about it before. Say a function that approaches 1 on the right and -1 on the left, that kind of thing. So anyway, where's the y-intercept here, guys? 1, very good. Now here's the nice thing about, oh, by the way, even. This is an even function. When you're dealing with an even function, you know the symmetry, right? We know it's going to be, I can fold my paper for a mirror image. So getting this middle section here is actually a lot easier now. Since I know it has to be symmetrical, there's not really any option other than for it to look like this. Louise? Like it can't do this, right? Well, for one, it can't pass through the x-axis. But 2, it wouldn't be symmetrical. It wouldn't have that even symmetry if I went like this. And of course, it could, I guess, maybe do this, but that would again require passing through the x-axis, which we know it can't. Right side would look like this. Left side is symmetrical. Are there any questions on how I got those 2 little pew-pews? No? Okay.
Okay. You guys know how to do